Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be continuing our discussion of kinematics by looking at sort of the first set of terms that we would encounter in kinematics, namely position, displacement, and distance. I'm mostly going to be focusing this on a one-dimensional kinematics discussion. And so let's get into all that. So first of all, what are these things? What do they mean? Well, position is basically where an object is located. You need really two things in order to define position. Okay, so what are those two things? So position, basically, you could say where an object is located, or what the object's location is, something like that. And you need a reference point, which is typically taken to be the origin. And you need essentially like a position relative to that reference point. So distance plus direction from the origin or reference to the object, and that's it. That defines position for us. We typically represent position like this. It's usually an X with an arrow over it. Sometimes we use an R with an arrow over it to represent position. Sometimes it's a Y with an arrow over it. Any of these are kind of like the common things used to represent position in physics. Okay, related to position, our next thing on the list would be called displacement. And displacement just is change in position. So if you have an object and it is at one location, and sometime later it's at another location, that is your displacement. So this is change in position. Motion from one position to another would result in a displacement. Now we typically represent this as delta x or delta r or delta y, delta z, what have you. And all that you need for this is the initial and the final displacement. So we could say initial displacement, which we might represent as like x I for initial, or x0 for x at time 0, etc. So, you could use R or Y or what have you. And then there's usually a final displacement. A final, I said displacement here, I mean position. Alright, and so the final position would just be like an X with a final attached to it, or an R final, Y final, what have you. And so your displacement equation might be given by, let's say, delta x is equal to, and really it's defined by, so I can put 3 bars to mean it's defined by these two things. It's your final position minus your initial position. So again, triple bar in the equal sign means defined as opposed to just simply equal to. So let's do a sort of conceptual example of this. Let's say that I have an observer standing over here somewhere watching everything. So observer at origin, and this origin is equivalent to x equals 0. Okay, now I have an object. Let's say the object is initially here, So object initial location. And maybe over here is the object's final location. Object final location. Okay. So my observer is standing here at the origin. This right here would represent my initial position. X, I'm going to use an I for initial. And this right here, from that same origin to where the object is located finally, this would be my final position. And my displacement from initial to final would be this arrow that points from the initial to the final and could be represented by delta x, which again is x final minus x initial. Okay, so that would be my displacement. Now, a quick aside about this vector notation. It's possible for, even in one dimension, for things to have like positive or negative direction to them. Okay, so this is sort of like example or conceptual example 1. So I'll call this example 1. And in this example, essentially all positions, x initial, x final, and the displacement delta x are all positive. Okay, so now let's do a second sort of conceptual example in which that may not be the case. So again, here's my observer. They're standing at the origin. So observer at origin. Maybe I happen to have an object which is initially here, object initial, location, and then maybe the object moves to somewhere over here. So object final location. If I wanted to do the, again, sort of positions and displacement, this arrow right here would represent my initial position. This arrow right here would represent my final position. And then the arrow that connects from initial all the way to final would represent my displacement, delta x. And it's still final position minus initial position. This is still true. Okay, so in some sense this begs an example with numbers. So example with numbers. Okay, let's write it out and then I'll do the example. That way you're not having to listen to me write and read at the same time, because that tends to be very slow. Alright, we have an object that is initially due east of the observer by 5 meters, and finally it is due west of the observer by 5 meters. So what's the displacement? Okay, first part of solving this, and really most problems in physics, is to draw yourself a diagram. Now you can do the math here without the diagram, but as a problem-solving tip, drawing the diagram is a very kind of important idea. So let's begin by drawing a diagram. Okay, in my diagram I just kind of need an origin or the observer, and I need an initial and a final location. I could maybe add in the vector arrows to show that this is x initial and to show that this right here is x final, the final position, the initial position. I could also maybe like identify these two things up here, initial and final. So initial and final. I'm taking, of course, the assumption that east is in this direction and west is in this direction. This other line, maybe the observer's lying down and this is north-south. Maybe he's standing up and this is up-down, and north-south is kind of in and out of the board. But we're mostly concerned with east-west. Now, generally speaking, we take things to the right as positive and to the left as negative. Okay, what does that mean for our purposes here? Well, that means that this initial, which was 5 meters due east, could be represented by, so an equal sign with a little dot over it means represented by, plus 5.0 meters. And this one at the final position could be represented by minus 3.0 meters, because it's to the left instead of to the right. We could also maybe draw our displacement vector. Again, that has to start at the initial and end up at the final. So here's my displacement vector delta x. Now delta x, recall, is the final position minus the initial position. So in representative terms, that would be minus 3.0 meters minus positive 5.0 meters. And from here it's just kind of algebra. We have negative 3 minus 5. That gives us a delta x, which is negative 8.0 meters. And if we wanted to be really thorough, we could say, well, 8.0 meters in our system can be used to represent 8 meters to the west. So that's sort of like translating back to the terms that we started with, due east, due west. This would be to the west or due west, something like that. All right, so that is displacement in one dimension. Now, we also need to talk a bit about distance. And distance works whether we're in one dimension or many. Distance is just how far the object has traveled. It's sort of like your odometer reading increase in moving an object from one location initially to another finally. All right, so distance variously gets represented by d, delta x, delta y, s. These are all different ways of representing distance in physics. Now notice that none of them have the little arrow over them that we had for position or for displacement. That is because distance, unlike these other things, is a scalar. So it's a scalar, not a vector. The other two, position and displacement, are both vectors. Now the magnitude of the displacement could be a distance. If I go back to this previous problem, for example, the magnitude of delta x would be 8 meters. So if my magnitude of displacement is 8.0 meters, well, that is the same thing as a distance, but it's not necessarily the distance that the object traveled in the problem. Because the object may have moved back and forth a little bit, it may have taken an arc to get from one location to the other, may have done some combination of those two things. So the distance traveled must be at least as big as the displacement, but it may be bigger. Put differently, the object, rather than simply moving from here where it started to here where it ended, may have done something like this, where it kind of like leaps from one to the other, or it may even have done something like this, where it overshoots and comes back, or may have done both. Either way, it turns out that the distance traveled by this object is greater than the magnitude of the displacement. So if we wanted to put some numbers to this particular example, if this arc is, let's say, like circular, so it's traveled through half a circle of arc to get from here to here, then the distance traveled is not just 8 meters, it's the circumference divided by 2, which would be 8 meters times pi divided by 2, the diameter being 8 meters. So you'd have 4 pi meters, or if you prefer, you would have 4 times pi, or 4 times 3.1415, etc. You'd get about 12.56, so call it 12.6 meters. To put numbers to it, if this object was moved along a semicircle, so half of a circle, then the distance that it travels through would be half the circumference of the circle. Now the diameter of the circle is the magnitude of the displacement, which is 8 meters. So the whole circumference would have been something like 25, a little over 25 meters, 25.13 something. And so half of that circumference would be the distance traveled, would be about 12.6 meters. Okay, maybe a second example is warranted with these same numbers. All right, for this example, we have an object which begins as before at 5 meters due east of the observer, and it ends finally as before at 3 meters due west of the observer. But in between doing that, it moves from 5 meters due east to 8 meters due east. So here would be 8 meters due east. It stops, it reverses directions, it ends up somewhere over here at 6 meters due west, stops, reverses direction, and finally ends up here at the 3 meters due west location. So how far has this thing moved? In other words, we're determining a distance here. Well, since the thing is moving along a straight line, we can basically just add up each of these little parts of the motion. So this distance right here would be adding, let's do this in green actually, we are adding a distance d, let's call it d1, from 5 to 8, so that would be 3 meters. Then from plus 8 to minus 6, we could call this distance d2. So d2 is 14 more meters. And then from here to the final location was from 6 to 3 is d3 is 3 meters. And so the total distance moved is basically just the sum of all these distances added on each sort of like leg of the journey. And so you'd have 3 meters plus 14 meters plus 3 meters. That ends up being 20.0 meters. So the distance traveled, d, is 20.0 meters, but the displacement magnitude, delta x, is still only 8.0 meters. All right, so I've given you basically two different examples in which the displacement and the distance traveled are not equal. There's actually only one way to make the two things be equal, and that is for the object to move in a straight line directly from its initial position to its final position. In that case, and that case only, the magnitude of displacement will be equal to the distance traveled. And that's all for today's video introducing these three concepts of position, displacement, and distance. hopefully you've learned something, or at least learned something that'll help you in physics. It may seem like semantics to those of you approaching it the first time, but the semantics sometimes do matter for us in physics. So in any case, I do hope that you have learned something, and thanks for watching.